Recall that an impulse or delta function is defined by two basic properties. One is that it's zero everywhere except at the origin, t equals 0. And the other is that it has unit area. That is, it integrates from minus to infinity, delta of t dt equals 1. So we draw these impulses as an up arrow, is a conventional notation, and the number next to the arrow, or sometimes the height of the arrow, is used to signify the area that's under that function. And we can get some insight into the behavior of this unusual function by viewing it as a limit of an well understood function. So let's define g delta of t as a function which has unit area, and it is delta wide, capital delta wide. So in this case, I have amplitude 1 over delta, and it's a square or rectangle function. And if you check the area under this, which is the amplitude 1 over delta times the width delta, is exactly 1. Well, if we take a limit of this function as capital delta goes to 0, we can view that as our impulse. So we can sketch that as follows. This is a series of functions of unit area, but decreasing width. So in the limit, as the width of these goes to 0, and of course the amplitude is going to have to go to infinity to get us a unit area under that signal. Now, impulses are mathematical defined functions. They don't really exist in the physical world, but they are good approximations or a good way of representing signals that have a very, very short duration and very, very large amplitude. But from our analysis standpoint, impulses are a very useful tool for describing different aspects of signals and systems. There are some very important properties of the impulse function, and we'll start with the sifting property. And the sifting property says that the integral from minus infinity to infinity of some function f of t times delta of t minus a, so we're integrating the impulse that is shifted by a units, in other words it occurs at time a, integrating that against this function f of t, and that will give us the sample of the signal f of a. Okay, so that'll evaluate f at time t equals a. The second property we're going to look at is a convolution property. And this states that if I convolve some signal x of t with a shifted impulse delta of t minus a, that the result will be the original signal shifted to the time at which the impulse occurs. So convolution with impulses is particularly simple. The third property that sometimes gets used is the scaling property of the impulse. And this says that if I scale the time variable, in other words, I replace t by at, what that does is it scales the amplitude or the strength of the impulse, but nothing else. And this only applies when a is greater than 0. So scaled impulses behave a bit differently than perhaps other functions, but it's because of this. They're this limiting version of a rectangle that goes to 0 width.